So in the last video, we talked a lot about integration over rectangles in 2 dimensions. We've got a theory of integration that's going to be good enough for our purposes, even if it isn't as powerful as Lebesgue integration, which you'll see in graduate school. But the problem with 2 dimensions, the reason why 2 dimensions is harder than 1 dimension. In 1 dimension, it's sort of reasonable to say, I want to integrate over intervals, and that's it. But in 2 dimensions, it's much less natural to say, I want to integrate over rectangles, and that's it. There are all kinds of interesting domains over which you want to integrate. You might want to integrate over a triangle or a pentagon or a circle, or you might even want to integrate over a rectangle, just one whose sides aren't parallel to the coordinate axes. So we're not going to be able to prove that you can integrate over arbitrary regions. That, in fact, is not true. But we're going to eventually build up to polygons. So let's start off with the following proposition. This is going to show we can integrate over certain special triangles. So we're going to start out with a rectangle whose bottom corner is the point AC, whose top corner is the point BD, top right corner. And so we saw in the previous video that if you've got a function that's continuous on the interior of this rectangle, everywhere in here you can integrate over the rectangle. Well, in this video, we're going to talk about a function that's continuous over half the rectangle, whose domain is a triangle that is half of your rectangle. We're going to show that you can integrate continuous functions over triangles, or at least these kinds of right triangles. So we'll start, T might be the bottom right triangle that I've drawn here. You can write that in this way. And then there are 4 other options. There is the top left triangle. That is this thing. Or there are, of course, the bottom left and top right triangles. Let's see, that first part is just a copy, and then we've got and its complement the top right triangle. I've forgotten a C plus up here. And the conclusion we want to draw is that you can integrate any continuous function. Any continuous function is integrable over this triangle, and a function whose domain is the triangle and whose range is the real numbers can be integrated. But the way we've defined integration, it really wants to be done in rectangles. And so we could write out a notion of Fubini integration, of integrating in both directions for a triangle, but we'd have to sort of write a slightly different thing for each triangle, and it wouldn't generalize very well to larger domains. So here is how we're going to just define or formulate integrating this continuous function f. We're going to define a helper function that's defined on the rectangle, because we know what we mean by integrating on rectangles. We're going to write f naught of xy. It's going to be f of xy as long as xy is in our domain of integration. And it's going to be 0 everywhere else. And then the integral of f naught really ought to, whatever you mean by the integral of f, it really ought to be the integral of f naught, because you're just extending f by 0. You're integrating f, but and maybe you're integrating some zeros too, but that's okay. The definite integral of 0 is 0. The conclusion, of course, is that you can integrate f naught in either direction. It is Fubini integrable. On this rectangle. In the sense we saw in the last video. Let's write out the proof. The first thing I want to note is that all of the one-dimensional integrals you need of f naught and the iterated integrals those all exist in the sense of a chapter 3. This is not too hard to prove, and it's pretty similar to the argument we had to make in the case of integrating a continuous function over a rectangle. The fact that it's a triangle doesn't make your life much more difficult, so I do not want to go through that again, but I just want to remind you that that is a thing we have to check. All right, now we're going to so all that's left really is to prove that the two integrals in the two directions, that it doesn't matter the order of integration too much, and we will prove that in the first case only. It's a little bit easier if you can write down concrete concrete formulas, but you can come up with a very similar proof in the other three cases. So now let's remember we're working in this big rectangle, and what we're trying to integrate over is this triangle T down here. And what we're going to do now is we're going to define a helper triangle. I'm going to be calling that dn because we're going to have a bunch of different ones of those. So let's define dn. So it's the upper left corner. So x is between a and b minus a minus b over n. And then y is between the formula for the upper bound of t. And then we add a 1 over n times the height of the rectangle. And y is expected to be between that and the top edge of D. And then T and dn are clearly closed. You all ought to be able to prove this by now. And now the function f naught, there's no reason to expect it to be continuous on the rectangle. It really ought to have a discontinuity here along the diagonal of t. But notice that dn is bounded away from the diagonal of t. So f naught, it's continuous on t by assumption, and it's continuous on dn because it's 0 everywhere on dn. So f naught, if you restrict it to the set T union dn, it is continuous. And you can prove that with a straightforward epsilon delta argument and looking at points in dn and points in t separately, and your delta will just be small enough to separate the two. Now, our triangle T is closed and bounded, and it's in R2. So by the Heine-Borel theorem, it is compact. So by some machinery in section 5.5, the Heine-Borel theorem and a bit easier corollary, we have that F is bounded. So that means it achieves its maximum, it achieves its minimum. You take the bigger of the two in absolute value. So we can say that there is a real number m positive real number such that f is less than or equal to m for all vectors v in our triangle. Now, remember we spent a lot of time on that one difficult homework assignment proving Ticci's extension theorem, and now we are going to use it. So we can extend our f naught restricted to this closed set which has two connected components. So let's call it Fn. Its domain, we might as well take it to be R2. So there is a continuous function. And Fn of v equals f naught everywhere, or in our restricted domain, which we can write as Fn equals f of v for all v in T, Fn equals 0 for all v in this other triangle Dn. And then the other thing Ticci's extension theorem gives you is that Fn is bounded. It's bounded between negative m and m for all v in R2. That is the constant that Ticci's extension theorem gives you. Ticci's extension theorem promises you a bounded continuous function, and you can check that the bound is the same bound as the function you started with. But if you're not quite sure, that you got the constants exactly right, you can let h be the bounded continuous function. Promised by a Ticci's extension theorem. And you can let Fn of v be whichever is smaller, m or h of v, except that you want to be at least negative m, h of v. And by, it's not quite by proposition 1.7.11, because all the propositions from section 1.7, they want your domain to be a set of real numbers, a subset of R, not an arbitrary metric space, but it's not a hard proposition to generalize. And so Ticci's extension theorem is giving us a nice continuous function that's 0 on our little upper left triangle and is the function we started with on our lower right triangle. It's not too hard to write down a formula for a function Fn that satisfies these properties, but we did do Ticci's extension theorem. We put a lot of work into it, so we might as well use it now. It makes this proof much simpler. And by homework 30, by the homework we did last time, Fn, because Fn is continuous, on this rectangle, we have that Fn is Fubini integrable, meaning you can change the order of integration, and all the conditions I don't want to write out about your one-dimensional integrals actually existing have to hold. So the two iterated integrals are equal, and everything you integrate on the way actually exists. What is it we want to prove? We want to prove that F naught is also Fubini integrable. Now, it's not too hard to check back, I'll leave that as an exercise that all the one-dimensional integrals for f naught do exist. They all boil down to integrals of continuous functions over rectangles. So I'm going to subtract fn on the inside. And then because integrals are linear, I can go ahead and just add to that. Add and subtract the integrals of fn of x, y. And then we can move them inside. Then we can break up the inner integral and then break up the outer integral by linearity. So this is indeed a legitimate equals sign. And then our first piece is going to have to just hang out there. And then because the fn is Fubini integrable, we can change the order of integration. And then I'm going to go ahead and subtract and add an f naught inside and outside. Now, of course, what we're trying to do is we're trying to show that this piece is in fact equal to this piece, which means we'd like to show that these two pieces up here are cancel each other out. Now, of course, they are going to cancel each other out, but we don't know that yet, so we're going to have to settle for showing that those two pieces, the pieces I've highlighted in blue, that they are small numbers and we can make them go to 0 by letting n go. Let's think about this first piece. So the integral, now let's bound these little error bits. So let's think about this integral first. Integral from c to d f naught of xy minus fn of xy dy. And we noticed before that exists, but that exists because fn is actually continuous and f naught is at least piecewise continuous. So let's draw our rectangle again. Let's put our triangle T on here. Our triangles T and D and I should say. And now we are integrating from C to D, which means we're integrating along either this line or maybe we're integrating along this line over here. And then we want to talk about and then we want to think of these three regions down here and in the middle and up here. We want to think of those separately. Let's label the y coordinate here. Let's call that c sub x because it depends on how far along you are. Let's label this one d sub x. Then up here, d sub x will just be d, and c sub x will still be the intersection with the top triangle. In one dimension, we can break this up, integral from c to c sub x, and then between c and c sub x, f naught, we're in the bottom triangle, so that f naught is just f of xy by definition of f naught. And then fn, we got it by extending f naught on the two triangles, so this is also f of xy. Then going from c sub x up to d sub x, integrating along this little bit. In this bit, f naught is already 0, and fn, well, fn of xy we have to leave as fn of xy here. And then between dx and d, that would be up here in the dn triangle. Both of our functions are 0. F naught is 0 because we're outside the bottom triangle. Fn is 0 because we want fn of 0 to be 0 on the top triangle. So the first two integrals are, of course, going to cancel out. One because you're integrating 0 in both cases. So let's put some absolute value bars around this. And then the integral from cx to dx, fn of xy dy. Let's put some absolute values so I don't have to worry about the minus. By proposition 3.1.10, that's at most dx minus cx. And then the supremum of absolute value fn. Then if you work out what dx minus cx is, it comes out to d minus c over n, or maybe less. It'll be less if you're up here. And then supremum of fn is, of course, m. And then, so if we take the integrated interval, that's at most the integral from a to b of d minus c over n times m dx. We're bounding the integrand and this inner integral here. And that, of course, is 1 over n times a bunch of constants. And you can write out pretty much exactly the same argument. You're integrating along horizontal slices now. That is bounded by exactly the same thing. So the two things we care about the two integrals of f naught in the two directions. That's less than or equal to 1 over n times, not quite the same mess of constants. You have a 2 out front. And this is true for all n, for all, say, natural numbers n. And the only way this can be true for all natural numbers n is if the thing you're taking the absolute value of is 0. Notice the thing in the absolute values doesn't depend on n. So we must have that the integrals in the two directions are equal, and that is to say f naught is Fubini integrable. So this idea in this proposition that we say something is integrable on a triangle if you can extend it by 0 and then integrate it on a rectangle, let's write that down. Let's let that be our definition of Fubini integrable on an arbitrary set. Let's let S be a subset of R2 and F be a function that is bounded and let F be a function from S to the real numbers that is also bounded. And we'll define f naught as the 0 extension as usual. F naught of v is f of v if v is in S, and 0 if v is not in S. And if, because S is bounded, it is contained in some rectangle. So if it's contained in a rectangle and f naught is what we're calling Fubini integrable, on the parent rectangle, we say that f is, that's what we mean by f is Fubini integrable. On S, and write the integral of f over S. That's the integral of f naught over a rectangle. And I will leave it as an exercise that it doesn't matter which parent rectangle you want. If S is contained in two rectangles, and you've got a bounded function f, then f naught is Fubini integrable on the first rectangle. I don't feel like writing this out, so let's go ahead and name these R1 and R2. If and only if f naught is Fubini integrable on the second rectangle, and if it is integrable on either and therefore both of them, then the two integrals of f naught are equal to each other. So it doesn't matter which of them you use to define the integral over S. And that's not too hard to write out. You just put your two rectangles in one bigger rectangle, and then you notice that all of the differences basically amount to a lot of integration of 0. That is, if S is this region, S is some bounded region, and you put S inside this rectangle, and you also put S inside this other rectangle, and you want to, and you integrate f naught, well, everything, all the extra bits, all the extra stuff you're integrating by integrating over this first rectangle, you're integrating 0 because f naught is 0 outside of S. And then all the bits you missed, all the bits that are only in this other rectangle, f naught is 0 out there. And so your integral is just 0. You don't have to worry about that bit. Another proposition that I think you will probably need on your homework. It's a little trivial. It might seem a little trivial, but it's good to have it under our belt. So let's let S be a subset of R2, be a single point, a line segment, and we're going to count the case where a line segment from a point to itself that is a single point. I do want a closed line segment. And let's let capital F be a function from S to the real numbers, and we're going to require that it be continuous. And the conclusion is that F is Fubini integrable on S. And moreover, what do you suppose the integral over S over a one-dimensional thing has to be? It's such a small domain, the integral just has to be 0. Here is the proof. What is a line segment anyway? A line segment is a segment between two lines, 2 points. So there are points A, B, and C, D in R2, such that S, that are the endpoints of S, that's the set of all t times AB plus 1 minus t times CD, where I'm multiplying by t, so it had better be a scalar, and to be a line segment, we restrict t to be between 0 and 1. I said closed line segment, so we include the endpoints. So here is AB, here is CD. Then we just draw the straight line between them. And then a single point would be if A is the same as C and B is the same as D. So we're not going to exclude that case. So the first case we look at, suppose the first case we are excluding single points. This is where it's a diagonal line segment, so it's not horizontal, it's not vertical. So let us let S be contained in a rectangle. We'll use the same rectangle in all the cases. For real numbers, alpha, beta, gamma, delta, with alpha less than beta, gamma less than delta. So in the first case, then what is our integral of f naught? So if x is in our first interval, then the integral of f naught, our extension, but 0 of xy dy. That means we're integrating over a vertical line segment like this. I'm not sure how far it extends, but it doesn't really matter because f naught is 0 except at this single point. And we happen to know what the integral of a function that's 0 except at a single point is. It is 0. That's by exercise 3.1.5. Because the function f of y, that's the one-dimensional function that's f naught of xy, is 0 for almost every point, is non-zero for at most one point. It could be 0 everywhere if your function f happens to be 0, or if your rectangle is a little bit bigger and you're integrating over a line segment that's over here. But it can't be 0 at more than one point, and we know the integral of a function that's 0 at all but one point is 0. And then, so... And also exercise 3.1.5 gives that this exists. So that's nice. So then the double integral, the iterated integral, that is 0. Because that is just the integral from alpha to beta of 0 dx, which is just 0. And then it's exactly the same argument in the other direction. You're integrating over horizontal lines. But again, you integrate over horizontal lines a function that's 0 at all but at most one point. So you get 0, same argument. So f is Fubini integral over s, and its integral is 0. So second case. This is the case where a is equal to c, and that is where we're integrating over a vertical line from AB up here to CD, which is the same as AD down here. I'm not going to require that B and D be different because I do want to allow us the one-point case. So in this case, if x is in our interval from alpha to beta, then either x is not equal to a, and when we integrate from gamma to delta, f naught of xy dy, that's integrating over some other vertical line that is 0, or x equals a, and the integral of f naught of xy dy. Well, I can't say it's 0, but we did say that f was continuous. That means f naught is piecewise is continuous. That is a real number by theorem 3.1.7. And then if we integrate in the other direction, we take the iterated integral. That means we're integrating a function. The inside, the integral here, that's a function of x that we're integrating. It's 0 except at one value of x. So just like in case 1, this is 0 by the same exercise, 3.1.5. And then if we integrate in the other direction, if y is in gamma delta, then we are integrating f of xy dx. That's integrating over a nice horizontal slice in this case. And that crosses our line segment at only one point. The integrand is 0 for all but at most 1 point. So we are getting a lot of mileage over out of exercise 3.1.5 in this case. And so in this case, the integral, the iterated integral in the other direction is also 0. The two iterated integrals are equal. And so f is Fubini integrable over s. Sorry, those should be integrals of f naught. So f is Fubini integrable over s, and the integral is 0. And case 3, which is the case where b equals d, is very similar to case 2. And that is all there is to that. And this video is getting long, so I will go ahead and tell you what your homework assignment is going to be. And it is going to be to show that you can integrate continuous functions over any polygon. You'll have to figure out how to write down what a polygon is. And the conclusion is that continuous functions are Fubini integrable. On polygons.